On Friday, we had a very almost philosophical lecture. And the second law can get like that. Right? It gets sometimes a little bit head in the clouds. So today's going to be pretty mathematical, but actually it's very practical. We're going to start moving from this very highfalutin concept of the second law towards useful equations that we can use, things that we can use to make predictions. So I'm going to tell you about thermodynamic potentials and equilibrium. I'm going to start off just by listing them. These are going to be presented without proof or motivation, although, we'll discuss. So the first one is what we already know now. For fixed U, entropy is max at equilibrium. Okay, so you already know that. All right, but there are others. There are other conditions and other potentials. So for fixed, entropy and volume the internal energy U is minimum at equilibrium. So this is a condition that you encounter in your introductory physics classes. They don't really state that, but that's the condition. Anybody, is there ever really a way to fix the entropy? Is there a way? How can we fix the entropy? There's no entropy reservoir. We can't connect the system to an entropy reservoir like we can with a pressure reservoir or a temperature reservoir. So I'll tell you, it's a little bit of an aside, but the only way to fix entropy is to be at 0 Kelvin. When you're at absolute zero, there's no entropy. So the physicists like it down there, but for the rest of us, it's not terribly useful. Okay, for fixed S and P, new term here, the enthalpy, H equals U plus PV, is minimized at equilibrium. Okay, so that's enthalpy. This condition, minimum enthalpy at equilibrium, is not terribly useful, but the enthalpy is useful. It's a useful thing. And one of the problems on the current P set is making a connection between enthalpy and the heat of a process. Sometimes those terms, enthalpy and heat, are actually used interchangeably. That's not strictly correct, but you'll see why. Okay. More. For fixed temperature and volume, so now we're getting a little more practical, right? Fixed temperature. That's something we know how to do. We all have thermostats. That's what your thermostat does. The Helmholtz F equals U minus TS is min at equilibrium. So I'll tell you, we spend almost no time at all on Helmholtz in this class because fixed temperature and volume are much less practical and useful than fixed temperature and pressure for materials processing. However, in other disciplines, especially in semiconductors, in semiconductor physics, it's the Helmholtz free energy that matters because your devices typically operate at a fixed temperature and your electrons are confined in the volume of the semiconductor device. So if we were to do things like calculate the theoretical limiting efficiency of a solar cell, we'd be worrying about Helmholtz. But as it is, you'll almost never hear us discuss that at all in the rest of the class. This is the one that matters. for fixed temperature and pressure. Anybody know what's the relevant potential for these conditions? Who's read ahead?
Gibbs free energy.
Gibbs, right. Right. So this is the one that matters for material science. And one way to see the rest of this class, actually the rest of the term, is we're just calculating the Gibbs for different scenarios. And we're doing price shopping for Gibbs, I call it. We calculate the Gibbs free energy for different scenarios, and we choose the lowest one as the equilibrium case. Okay, so that is thermodynamic potentials. Now, these are presented without proof. It's not worth the time here to motivate each and every one of those. On the P set, you're going to convince yourselves that given this, then this. So one of the exercises is going through a form of proof of this. And that's useful because Gibbs is the one we care about. Now, I have to make some mathematical asides because without this, my math note, a lot of what comes is kind of weird and confusing. So in 3020, state functions, I'd say state variables, are functions of at most 3 independent variables. And most 3 independent variables. And this is where that comes from. It comes from, sorry, this pen is kind of smushy. It doesn't come from nowhere. It comes from the combined statement. So it comes from physical reasoning. Right? du equals T ds minus P dV plus mu dn. This implies the existence of a state function. U is a function of S, V, and N. This is a critical link here. If you write down a differential form, we're going to learn how to identify the independent variables, the coefficients, and the dependent variable. And the existence of this differential form implies a state function. Now, in most cases, we may never know this, but we can still use this. That is, we may never know the closed form of the state function, but we can still use its differential form. In fact, outside of the ideal gas situation, we almost never write down any state functions in this class. You can't find a complete state function for something useful like a high entropy alloy. It doesn't exist. It's too complicated. All right. So a corollary of this is that thermodynamic potentials have what I'll call natural independent variables. Which we will see aplenty in the case of Gibbs. So for example, entropy is a function of energy and volume. If you remember, at equilibrium, entropy was max for fixed energy and fixed volume. that tells you that those are its natural variables. At equilibrium, internal energy was maximum for fixed entropy and volume. Those are its natural variables. Enthalpy was equilibrium for a minimum at equilibrium for fixed entropy and pressure. Those are its natural variables. For Helmholtz, its natural variables are T and V. And for Gibbs, its natural variables are T and P. And before you ding me here, I'm not writing the N's for compactness. So everything is also a function of the size of a system. I'm just leaving that off to keep the lines short. Okay, one more note. Where on earth does this stuff come from? When I learned thermo, these potentials were just told to me the way I just told them to you. And it was and I think in the back of my mind, I said, where does that come from? And then I forgot the question and I didn't come back to it for years. It does come from somewhere. The potentials are related by change of variables. Via Legendre transforms. So this is something we don't have time for in this class, and probably I wouldn't be able to teach very well anyway. This is a math concept. And so for those of you who've seen Legendre transforms in your math classes, that's great. For those of you who are curious, you could start with the wiki entry. We're not going to cover it in detail. You can think of it as just one more type of a transform, like a Fourier transform or a Laplace transform. Right? The Fourier transform, for example, changes your natural variables from time to frequency. That's an example. Legendre transform will change natural variables, for example, from U as a function of S and V to H as a function of S and P, exchanging V for P. And if you'll remember, H equals U plus PV. And this comes from somewhere. This is all beyond O2O. I just wanted you to know it comes from somewhere. Right? It comes from somewhere. For most of the class, you can just memorize. Okay. Let's dive in a little more. All right, let's start with the combined statement. du equals T ds minus P dV plus mu. I'll let this be a multi-component system, so I'll keep the labels there. Okay. Somebody please remind me, what are the independent variables in this differential form?
S, V, and Ni.
Right. Those are the independent variables, right? The other things we call, having fun with colors today. The other things we call coefficients. Okay. So the coefficients describe how the dependent variable varies with the independent variables. And we can write down by inspection coefficient relations. And here they are. du ds. du ds at fixed volume and fixed particle number equals what? What is partial U by S? You can
T.
pick it off of T. Yep, you just look at the equation, look at the differential form, you pick these off. du dv at fixed entropy and particle number equals minus P, and du dni at fixed entropy, volume, and particle number J not equal to I equals mu I. So these are coefficients. They're called. I mean, you can call them, oh, I just picked partial differentials, but they're called coefficient relations. A lot of problem solving in thermo comes down to calculating these coefficients. The most chapter actually in get to chapter 10 of the book. The most useful chapter is chapter 4. If you read only one chapter of this book, chapter 4, because it contains all the things we need to actually solve problems. To actually solve problems, you just have to understand chapter 4. And I say just, it's actually one of the hairier chapters, but there it is. And it's all about these coefficient relations and identifying and choosing independent variables and calculating coefficients. So let's see how to do that. I wouldn't have called it strategy. I think it's a little funny, besides it's a tactic, not a strategy, but that's what it's called in DeHoff, so I'll stick with it. The general strategy for deriving thermodynamic relations. This is really best illustrated by an example, so that's what we're going to do. Here is the general problem. The general problem statement. Given a dependent state variable, Z, independent state variables X and Y, calculate. All right, so this is a word problem. Delta Z for a given process. So this is like, probably half of all thermal problems boil down to something like this. There's some dependent state variable, which you identify through the problem statement. There's some independent variables, which usually you're not told. You figure them out through the problem statement or the situation in hand, and you want to calculate the change for a given process. So what example are we going to do? Example. Calculate delta V for a process involving a change of pressure at fixed entropy. Which is also a reversible adiabatic process. This is helpful. Remembering that fixed entropy and reversible adiabatic processes are related. That's really helpful. Okay, so now I'm going to step through this example. we want to write down the differential formula that describes the change in the dependent variable. And this is going to depend on some coefficient times dp plus some coefficient times ds. And our job is to find those coefficients and then integrate right. This is the approach. Once you find these coefficients, then you can integrate this term, which for fixed entropy gives you the thing you're looking for, which is the change in volume. That's what we need to do. Questions before I go on to actually do that? Okay. So we're going to start. 1. We're going to write the exact differential. It's rewriting what we did, right? dv equals x dp plus y ds. X equals dv dp at s. Y equals dv ds at p. Okay, good. And then we're going to do a change of variables. There's a really useful reference to Hoff table 4.5 to express dp and ds in terms of dp and dt. De Hoff chooses P and T because it's a material science text. Another text might have chosen a different two. You could choose any two. So we're going to look up in table 4.5, and it has the coefficients for every state variable as a function of dp and dt. So here, this is trivial, right? There's going to be no, this is 0, because dp equals dp. That's trivial. The entropy is non-trivial. We could derive this, but we're not going to take the time. We're just going to copy it from the table. It happens to be equal to Cp over temperature times dT minus V alpha dP. That's not obvious to me, right? I have to think about it. This I could figure out if I thought about it long enough. This it doesn't make sense to me. I just have to derive it. But you don't have to derive it or think about it. It's right there in the table. So here is pressure and entropy written now as dependent variables, dependent on temperature and pressure. Okay, so we're going to combine now, and we get the following. dV equals x. I'm going to combine. Equals x dp, right? That's easy. Plus y. What's ds? ds equals Cp over T dt minus V alpha dP. But I just plugged in, substituted for ds here. Okay, so that's the second step. Then I'm going to collect terms. The third step is collect terms. Collect terms. So I have the following. I have dV equals y Cp over temperature dt plus x minus y V alpha dP. Okay, I still don't have X and Y. I still don't know what they are. But I can say by inspection, dV dt at fixed pressure equals y Cp over T, right? That's this coefficient. dV by temperature at fixed pressure is that coefficient. And dV dP at fixed temperature equals this coefficient, X minus y V alpha. I say we get the coefficients by inspection. The fourth step is you compare to the known coefficients. Again, referring to table 4.5. So in table 4.5, you will find the differential form of volume written as a function of temperature and pressure. And this is what you'll find. V alpha dt minus V beta dP. So here's the thing. This coefficient and this thing have to be equal. And this thing have to be equal. Because they're both the same mathematical objects. They're these partials. If you say if it walks like a duck, talks like a duck, it's the same thing. So compare to known coefficients and equate. So we're going to equate. We're going to equate them and we're going to get the following. dV dt at fixed pressure, well, that was this, right? Equals y Cp over T, but it's also this, equals V alpha. And dV dP at fixed temperature equals this, X minus y V alpha, but it's also this, equals minus V beta. So now we have our answer. How? We have a system of two equations and two unknowns, X and Y. Two equations and two unknowns. So now you can solve. 5, solve for unknowns. And I'll spare you the algebra there because it's pretty easy. Solving for y, V alpha T over Cp, and solving for x equals V squared alpha squared T over Cp minus V beta. And these are complicated and non-obvious, right? That's why you need a set of tactics to get to these answers. Because if you follow this approach, you will always get the right answer, even if it doesn't make sense to you. So here's the final answer. dV equals V squared alpha squared T over Cp minus V beta times dP plus V alpha T over Cp times ds. This is the thing we were looking for. That's it. We integrate this to find change delta V for given delta P at fixed entropy. Again, this is mechanics, right? This will work for you, even if you don't have a physical intuition for every step. this strategy works. Question. For a real material, when you are, okay, this is very realistic. I mean, now we go from sort of multivariable calculus to money on the line, right? You are calculating the effect of a pressure change on the volume of components. Let's say you're going to send this into outer space, and you have a system made out of components, and the components are made out of materials, and you want to make sure that the pressure change that your device experience isn't going to cause the thing to fall apart. So now this matters a lot. You need to know how to do that calculation. Here's how. Question, where are you going to get these, this is the integrand, right? How are you going to evaluate the integrand? How are you probably going to end up evaluating the integrand when you're working at SpaceX and you need the answer in 5 minutes? Okay, let me set up a straw man. Are you going to do density functional theory calculations to calculate the thermal expansion coefficient and specific heat and volume and compressibility for your material from first principles?
You're going to probably look at databases.
Databases, thanks. That's like my favorite word. You're going to look at databases. This stuff is in databases. You're going to parameterize what you need using databases. You're going to plug that in, and you're going to do this integral numerically. The computer is going to do it for you, right? You're going to make sure you have good sources of data. You're going to make sure the data is inputted correctly. You're going to make sure your units are right. And then the computer is going to do this for you as a numerical integration. That's how it works in the real world. So this sort of hairy looking challenge is why we hammer on this stuff in O2O. And we make you talk to, you get to meet the librarians and such, because being able to go from those data resources to answers, right, is really an important skill. It's really an important skill. All right. There is one case where you don't need to do any of that. And we'll discuss this a little more in next lecture. And you can work this out, on your own if you're curious. It's also worked out plenty in the textbook. For an ideal gas, as with many things, it simplifies. So you don't need any databases to evaluate this for an ideal gas. It simplifies to the following. X equals minus V over P times C P minus R over CP is also equal to V over P C V over CP. And this leads to an expression which before we just gave you, P final over P initial equals V initial over V final. So this is where that comes from. If you use this expression for adiabatic process for an ideal gas, it comes from this. So I'm not going to take time to derive that now. It's kind of an interesting calculation. You can just evaluate all this stuff. And I'll just mention that in PSET 2, you're doing a related problem, which is you're calculating change in Gibbs free energy with pressure and entropy. So we just did volume with pressure and entropy. And in PSET 2, you're going to do Gibbs with pressure and entropy. But the overall, what they call the general strategy, is the same. Okay. So for the remaining minutes, we're going to get a little bit specific and talk about Gibbs free energy. Let's talk about equilibrium. Fixed pressure and temperature. So now we're processing materials. Gibbs free energy equals U plus PV minus TS is minimized. Let's play with a differential form, dg. So I'm going to use the chain rule. dg ds minus s dt. And that was just chain rule. And now I can use the combined statement. du equals t ds minus p dv plus mu of I dn of I. Right, that is all du. And I carry the rest of the terms. Plus p dv plus v dp minus t ds minus s dt. So here I use combined statement. And I'm going to see a bunch of things cancel, right? I'm going to see a bunch of things cancel. So we have TDS cancels TDS minus PDV cancels PDV. And so this simplifies a little bit. And I get the following. Equals minus S dt plus V dP plus mu I dn of I. Good. This is what we wanted, because I told you the natural variables for Gibbs were temperature, pressure, and particle number. And that's what we get. That's what the calculus gives us. So there's a little clue there into how the Legendre transform works, but again, we won't go there. So the independent variables are T, P, and N sub I. And what are the coefficients? Somebody, please?
S, V, and mu I.
Right. Minus S, V, and mu of I. I'll make a note here. A lot of times in this class, I use implicit summation. You probably picked up on that. But this implies I, mu of I, and I. Just a little bit more compact. Right? There's no I index on the left-hand side, so that means it has to resolve on the right-hand side. So you implicitly sum. Right. And by inspection, minus S describes the change of Gibbs with temperature at fixed pressure and particle number. Volume describes the change of Gibbs with pressure at fixed temperature and particle number. And finally, our favorite, chemical potential, describes the change of Gibbs with particle number I at fixed temperature, pressure, and particles J not equal to I. So already we can say something about the slope of these things. On a slope of, let's see, here's pressure, and here's Gibbs free energy, and we're fixing temperature and particle number. What's the slope? What's the slope? Is it positive or negative? Gibbs versus pressure for fixed temperature and particle number.
It's positive.
Positive, because volume is always positive. Can't have negative volume. All right, so that's good. Being able to pick off the slope and the curvature of these things is really useful. It's really, really useful, as you'll see. What about this? What about temperature? Change of Gibbs with temperature for fixed pressure and particle number.
Negative.
Yeah, it's negative because entropy is strictly positive. So negative entropy is strictly negative. You have to think about these slopes. The Gibbs free energy increases when we squeeze. That's related to the enthalpy. That's related to the enthalpy. When we squeeze something, we're increasing the energy content of all the bonds that make up that thing. When we squeeze something, we're increasing the entropy content of all the bonds that make up that thing. So this is Gibbs free energy getting higher as we squeeze. When we heat something, Gibbs decreases. When we heat something, we're increasing the entropy. We're increasing the amount of mixed upness. And Gibbs depends negatively with entropy. We'll see this in many examples. Okay, so up with pressure, down with temperature. What about conditions that we're interested in? At fixed temperature, T, at fixed temperature and pressure, dt equals 0. That's pretty easy. And dp equals 0. That means the equilibrium condition reduces to dg equals, let's see, minus s dt plus v dp plus mu by d n of I. And we're holding that fixed, and we're holding that fixed. That means it basically reduces to this equals 0, right? Because G is min at equilibrium. So if you think back to calculus, when you would calculate extrema, right? The extrema positions of a function are where its slope is 0. So equilibrium condition is that the change of Gibbs with particle number I is 0. So for most of the cases of interest to us as practicing material scientists, that is multi-component heterogeneous systems, this becomes dg sum over I component k dni component k. I'm introducing a new notation here. Superscript labels phases. And the subscript labels components. And so now we can picture something in our minds. We have a phase boundary here, 2 phases, and each phase has 2 components. Right. This was a purple-rich phase, and this was an orange-rich phase. And evaluating the equilibrium condition is going to come down to knowing how the components can exchange between phases and what the effect of that exchange is on the chemical potential. Let me write that out. Okay. What determines whether or not components can exchange between the phases? It's the boundary. So the property of the boundary tells us what components can exchange between phases. And that can be engineered. So there's a lot of engineering around choosing boundaries to get the desired equilibrium condition. But much of what comes later in this class is calculating composition dependence calculating the composition dependence of those chemical potentials. And we're going to develop models for that and graphical tools for that, finally leading to binary phase diagrams. All right, one last note. I want to do one last note about independent variables. Sometimes called natural. If a state variable is regulated, what does that mean? Controlled. Right? Regulations are controls. If you go to a McMaster car, you can buy a regulator for pressure. If you go to Home Depot, you can get a regulator for temperature. We call it a thermostat. And those things that you would buy have analogs in you know, not the real world, but in R&D and material science as well. If a state variable is regulated, that's why I'm using that term, because it'll help you in the future. If it's regulated, then it must be independent. So choosing your independent variables is one of the major intellectual challenges of thermo. It helps to even know that that's the challenge you're facing. Knowing that that's the challenge you're facing, it gives you a good start. Identifying independent and dependent variables from the problem at hand that's key to success. So for example, if the problem statement says something about fixed pressure, then you need to choose pressure as an independent variable. Right. If the problem says adiabatic, right, you need to choose what should be your independent variable if the problem statement said adiabatic? What should be one of your two independent variables?
Entropy?
Yeah, entropy. And if the problem statement says in a thermal bath, then you need to choose temperature as one of your independent variables, and so on. So this is like a key for turning problems that you encounter on problem sets or in the real world into things you can solve using thermo.